Hello everyone, my name is Osamu KUWAZURU. I'm working in the Department of Nuclear Safety Engineering. The name of the department is different depending on the program. So when you take an entrance exam, please confirm the name of corresponding department. Here, I'd like to talk about the stress corrosion simulation for precise plant life assessment. Maybe you don't know the term stress corrosion. This is a phenomenon in which the corrosion is promoted by the stress or deformation of the material. This is an interdisciplinary study between mechanics and chemistry, and this is an important issue that we face in the maintenance of nuclear power plants. So we are developing a new simulation technique to evaluate the stress corrosion. First of all, I'd like to introduce my laboratory. My major field is the mechanical engineering, especially the computational solid mechanics. And in my career, it expanded to the nuclear engineering. The related fields are solid mechanics, fracture mechanics, electrochemistry, and numerical analysis. And now I'm interested in the interaction between corrosion and fracture. So now I'm studying the electrochemistry. And for class information, I'm providing these four classes in undergraduate course and graduate courses. This is a background of study. This figure shows the pressurized water reactor, PWR. This is a reactor pressure vessel, and this is a steam generator. And the nuclear fuel is here and generates a lot of heat. The primary water receives its heat and go to the steam generator, and the heat is transferred to the secondary water. And the secondary water is boiling here, and its steam go to the steam turbine and generate an electricity. The reactor pressure vessel is made of low alloy steel, and the core internal structures are made of stainless steel. And these components are manufactured by forging and welding. And the weld is most important part because it is vulnerable to cracking. So the primary system is subjected to the severe condition, such as high temperature, about 15 megapascal, and high temperature of over 300 degrees C, and also the neutron irradiation from the nuclear fuel. As an aging effect, we have to consider the fatigue, corrosion, and irradiation embrittlement. So it is important to conduct a precise plant life assessment, that is, the inspection and evaluation and repairs. And my research will contribute to improve the accuracy in the evaluation of corrosion. This figure shows the longitudinal section of the welded pipe. The welded metal is poured here, and two pipes are joined. In the welding part, there is a high residual stress due to the welding. And this residual stress is generated by the shrinkage of welded metal during the solidification process. And next to the welded metal, there is a heat-affected zone. In this area, the material is hardened by the welding heat. So most of failure occurs in hearth. So if the defects or damage exists on the inner surface, the chemical reaction with coolant water is activated and the corrosion begins. And that corrosion leads to cracking like this. And this crack grows into the material by the corrosion. So this is a mechanism of stress corrosion cracking. And basically, the stainless steel is a corrosion-resistant material. But if the bad environment and high stress are imposed simultaneously, then the SCC happens. Let me summarize the mechanism of SCC again. First, the surface of stainless steel is covered with the oxide film, that is the passive film of chromium oxide. This film is very strong and protects the material from the corrosion. But if a plastic deformation occurred like this, the plastic slip occurs and oxide film breaks. Then the new surface appears like this. And this new surface is not covered with the oxide film. So the chemical potential is different between the new surface and oxide film. So this difference in the potential leads to the chemical reaction. The anodic reaction occurs on the new surface, and the cathodic reaction occurs on the oxide film. As a result, the material is dissolved from the new surface with a cathodic reaction on the oxide film. This is a corrosion, and sometimes leads to a stress corrosion cracking, like this. And this is a mechanism of SCC. This slide shows the objectives and methods. We have some difficulties. First, the nuclear reactor environment is hard to reproduce in laboratory. Next, corrosion occurs in long time range from days to years. So the experiment is not easy to conduct, and the experiment is very costly. So we want to utilize the numerical simulation instead of experiment. And last one is that the damage of oxide film is rapidly repaired by the repassivation. This is a good property of the stainless steel, but in mathematical viewpoint, it is complex because the damage is time dependent. So the objective of study is to clarify the interaction between stress and corrosion by using the numerical simulation. So we have to develop a numerical simulation technique for the stress corrosion problem. The new technique is required. Then we need an electrochemical property for the corrosion simulation. So we have to obtain the electrochemical property dependent on the film damage to be used in the corrosion simulation. As a methods in the simulation, we use the boundary element method to solve the electric field in the electrolyte and evaluate the corrosion rate on the surface. And in the experiment, we employ the rapid tensile test in corrosive environment to evaluate the effect of film damage on the electrochemical property. This photograph shows the tensile test in the NaCl solution. This is the tensile specimen, and black part is the coating. So this part, only this part is exposed to the NaCl solution. And to measure the strain, we are employing the immersible extensometer like this. This slide shows the results of experiments and calculations, simulations. The vertical axis is the current density. It means the rate of chemical reaction. And horizontal axis is the potential of the material. And this V-shaped curve is the polarization curve. And here, the current density is 0. And this point is called the natural potential. And left side of curve is called cathodic curve. And right side is called anodic curve. And the corrosion is related to this anodic curve. So the anodic curve is important to evaluate the corrosion behavior. Without stress, we can measure this polarization curve like this black line. And the plots are the results of rapid tensile tests in this study. And this figure shows the effect of damage on the polarization curve. So damage increases, then the curve is shifting to the left side. So the natural potential decreases and current density jumps up 1000 times. So this indicates that when the oxide film breaks, the corrosion becomes easier and the corrosion rate becomes faster. And in the result of simulation, we can see the similar results. So we gave two different polarization curve to the damaged surface and oxide film. And damage is located at the center of the surface. And this model is employing the periodic boundary condition. And then we could obtain this kind of distribution of potential and current density. And we can see very high potential and very high current density around the damaged surface. So this kind of simulation gave this kind of polarization curve. And then we can see the similar results, that is the decrease in the potential, natural potential, and increase in the current density. So experiment and calculation shows a good agreement qualitatively. So now we have the polarization curve depending on the damage of oxide film. So we can perform the electric analysis for any stress condition. So we can evaluate the corrosion rate in any stress condition. So this is the starting point of the stress corrosion simulation. Finally, I talk about future prospects. Now we can evaluate the current density around the damage induced by the stress or deformation. So now we have the current density distribution on the surface. So the next step is to trim the surface according to the current density distribution. So this expresses the pitting corrosion. At this time, the metallic ions are eluted into the electrolyte, and these ions are moving and diffusing according to the electric fields and fluidic flow. So we need to consider this kind of ion movement, ion transportation. At the same time, the electrons move to the oxide film, and a cathodic reaction occurs here. And sometimes this this results in the deposition of corrosion products. So we need to consider the change in shape by the pitting and deposition. In summary, for complete simulation, we have to consider the stress and deformation and fluidic flow and metal dissolution. This is a chemical reaction rate, and the electric flow. This is a mass transport and ion transports. And finally, the pitting and deposition. This is a moving boundary problem. This is also a difficult problem to be solved. So totally, the stress corrosion simulation is highly complicated multi-physics problem. So this is very hard to solve. So that's why this stress corrosion is a very interesting problem. So we are welcoming you to join this study. So please join this challenging study and be a pioneer of the simulation together. So if you have questions, please contact me. And we are waiting for you. Thank you for your attention. Bye bye.